I'm going to start this lesson off by looking at the covalent bond between two hydrogen atoms. We know this as hydrogen gas, H2, but we've never specifically looked at the bond between them. Remember, in a covalent bond, electrons are shared. This is different than ionic bonds, where each ion possesses its electrons and they're attracted to each other through a strong electrostatic force. In covalent bonds, there are electrons that are being attracted by the other proton of the other atom, and they are bound together by this shared group of electrons between the atom. Our most simple bond would be hydrogen. Each hydrogen atom in its neutral state has one electron as well as one proton. When they form a bond, they will share the two electrons between them. And it will come together like this. These two electrons sit equally between the nucleus of both of these hydrogen atoms. This is called a covalent bond. Co meaning together, sharing, and valent referring to the electrons, covalent. In the Lewis dot model, which is what I'm showing here, the electrons are represented as dots. You can also represent them as line structures, where you put a line between them like that. One single line represents sharing of two electrons. That's called a single bond. Hydrogen is easy because each hydrogen only contains one electron. So let's look at what happens when we have more than one electron, because every other atom has more than one electron except for helium. What we're looking at and what we are drawing are Lewis dot structures. These are models of covalent bonding, and they are based on octets, which are groups of 8. You have seen this type of modeling before on IC 2020, on the Lewis dot models, and on the Crown Jewels games where you put them together and make bonds. Now we're going to learn how to do it on paper. Imagine that every atom is a square table and there are 8 seats at the table around it. Some are filled with electrons that the atom possesses, and some are shared with the atoms that are around it. Every X represents an electron, and so when the table is filled, there will be 8 electrons total around the table. This is the way your table is set up, with 2 electrons on every side. That is the amount of electrons that can be held by the bench around this square table. You can have 1 there, or you can have 2, but there will never be 0. There will always be at least 1 electron on every side of the table. That is because, very importantly, only nonmetals form covalent bonds. Aluminum is not going to form a covalent bond, so you'll never have less than 4 electrons around the table. Let's do an example. Hydrochloric acid, HCl. There are 2 atoms involved in this bond. There's chlorine and there's hydrogen. The first thing to do is to determine how many seats are filled on their tables. That is to say, how many electrons surround hydrogen and chlorine in their neutral state. We can tell from the periodic table. If you look at the top of every column, you will see a Roman numeral. For our nonmetals, this will tell you how many seats are filled around the table for a neutral atom. For hydrogen, that would be 1. Everything in the 2 column is a metal, so it's not going to form a covalent bond. Same for the third one, we're going to ignore that. Then we jump to carbon. Carbon's Roman numeral is 4. There will be 4 seats around carbon. 1, 2, 3, 4, like that. Nitrogen is 5. 1, 2, 3, 4, 5. Oxygen is 6. 1, 2, 3, 4, 5, 6. Fluorine and everything below it is 7. 1, 2, 3, 4, 5, 6, 7. That applies to everything in the column. So everything here, everything here, everything here. They're all the same. You might start to see the genius of the organization of the periodic table. We are interested in chlorine, which is 7. 7, and we know hydrogen is 1. So now we have to draw them. Chlorine gets 7 electrons. 1, 2, 3, 4, 5, 6, 7. It doesn't really matter where you leave the open one as long as there is only one that is missing a pair. Hydrogen, only one. These will form a bond where they both have open spots in the table. There are 2 shared electrons. This is a covalent bond. We can see that chlorine has 8 electrons surrounding it, and it has a complete octet. A full table, if you will. The object with every Lewis dot model that you make is to complete the tables. Let's do one more example. Water. For water, I'm going to start with oxygen. Go look at the periodic table, look at the Roman numeral for oxygen, and determine how many seats oxygen has at its table. The Roman numeral in front of oxygen is 6. That means it has 6 spots at its table. On your paper, draw how you think oxygen's electrons should be arranged. Do that now. There are 2 options for how you decided to arrange your electrons. Either like the top choice or the bottom choice. Either you have an empty spot here or you have empty spots here. If you drew this, that is wrong. There should be no empty spaces. Empty is bad. No, 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 no empty spaces. There should be at least 1 electron on every side of the table. There's no way for it to make a bond if there is a completely empty slot. A bond has to be formed between 2 electrons that are being shared. Has to each bring 1 to the table. So let's do water. Start with oxygen, and I'm going to arrange it so I can put my hydrogens on either side. We can see that there's a spot for a hydrogen here and a spot for a hydrogen on the other side, and we have water. Let's draw the line structure. There it is. 2 single covalent bonds between hydrogen and oxygen on both sides. Last example, NH2F. I'd like for you to pause here and draw what you think is the Lewis dot structure for NH2F. In chemistry, oftentimes, the way that a molecule's formula is written is indicative of the bonding structure. What starts at the front makes the first bonds, and depending on what comes after it and the amount of bonds that that atom can make determines kind of how the bonds are being made. And you'll see that more with different structures. You'll notice that the carbons aren't all written together, like CH3, CH3. You might be thinking to yourself, why isn't that just C2H6? Well, this tells us about the structure of the bond. I'm going to start with nitrogen. And when you're drawing your Lewis dot structures, you really don't need to draw the square around it. That was to show you the table aspect to it. So nitrogen has 5 electrons surrounding it, and we know that hydrogens each only make 1 bond. So I'm going to put those into the empty slots. And then my fluorine has 7 electrons around it and 1 open spot, and there is 1 open spot left on my nitrogen. So that is where my fluorine will go. You need to look at the amount of electrons and the amount of bonds that an atom can make, and not so much that these are written in a row, so to speak. Because if you were to bond it in this way, you would end up with something maybe like this. And that would just be horribly wrong, because hydrogen can never make more than 1 bond. So it's important to look at how many electrons are around each atom and then make the bonding accordingly. Good luck!